Hello everyone, I'm Miaozhang. I'm very glad to share our paper towards Cloud Edge Collaborative Online Video Analytics with Fine-Grained Serverless Pipelines. Let's start from a brief introduction to video analytics. The ever-growing camera deployment and the advances in computer vision algorithms have boosted the development of video analytics. By applying various algorithms to the video content, it can answer users' queries about spatial and temporal events occurring in the video streams. I'll show you two representative video analytics pipelines. The first one is a vehicle pipeline, which can answer queries like how many cars were passing through the camera's field of view during rush hours. And the second one is a face pipeline, which can classify the age and gender of customers appearing in a store's camera. Both pipelines are composed of several basic vision primitives, such as the vehicle detector and vehicle tracker in the vehicle pipeline. These typical primitives in video analytics are notorious for high resource demand, especially when DNN models are used for high accuracy. Tremendous efforts have been made to achieve high-performance video analytics in recent years, from retrospective video analytics on large video datasets to real-time video analytics on live video streams. In order to meet the stringent latency requirements of live video analytics, edge resources have been explored. However, resources at the edge are usually limited and can support resource-intensive live video analytics. As a result, Cloud Edge collaborative systems are designed to have the best of both worlds. A variety of techniques arise in this context to reduce network and computational resources, such as DN model compression and approximation, frame filtering, frame compression, and DN model splitting. Despite their promising results, most of them manually allocate and manage coarse-grained resources, for example, at a virtual machine level, and their monolithic deployment architecture unavoidably hampers scalability and flexibility. To acquire a deep understanding of real-world video analytics characteristics and motivate our system design, we first conduct a measurement study on two real-world camera streams. The first one is a traffic camera mounted at a crossroad. We focus on the vehicle behavior in the stream. The other camera is installed at the entrance of a roadside restaurant. We are interested in human faces appearing in its video stream. We first examine if there are always objects of interest in camera streams, and find that a considerable part of frames don't contain any useful information. This indicates provisioning dedicated resources to analyze a stream is unnecessary, and the resource efficiency can be significantly improved by developing content-aware resource schedulers. We further investigate the number of objects of interest varies over time. As shown in the figures, the number of objects of interest changes over time in fine granularity. Such fine-grained video content dynamics can hardly be captured by one-time offline profiling or coarse-grained online profiling. Therefore, fine-grained profiling or prediction is needed to adapt to the video content and achieve the most benefits. Fortunately, we can also observe certain fine-grained temporal correlations, which indicates time series dependency information may be useful. Primitives in a video analytics pipeline are coupled with each other tightly through video content. It's interesting to see how the input data size of each primitive changes as the video passes through the pipeline. As shown by the figures, the input data to primitives dramatically decreases as the video goes down the pipeline. Also, the input data size of each primitive is influenced by video content dynamics. This indicates compared with streaming all videos to the cloud for analysis, Cloud Edge collaborative schemes may significantly reduce network resource consumption. To achieve the most benefits of Cloud and Edge collaboration, video content dynamics should be also taken into consideration. The measurement insights inspire us to introduce serverless computing in Cloud Edge collaborative video analytics. Serverless computing, represented by function as a service offerings, has gained increasing popularity in recent years to build various applications. As the cloud extends to the edge, serverless functions can also be executed in CDN and IoT devices. Serverless functions opens up new opportunities to overcome the disadvantages of current video analytics systems. To be specific, compared with a virtual machine, the function is a much fairer resource unit. It can help address the fine-grained video content dynamics. The scaling up or down of resources is automatically driven by the input workloads, which can handle unpredictable or bursty video queries, thus avoiding unnecessary resource provisioning. Its microservice deployment architecture decouples monolithic application code into a set of standalone functions, which can improve flexibility and scalability. Given these benefits, we accordingly propose Serverless, a Cloud Edge collaborative video analytics system empowered by fine-grained serverless pipelines. Serverless is a serverless-based system that involves users, a controller, an edge node connected by cameras, and the cloud. For illustration purpose, we assume there are 3 cameras continually streaming their captured videos to the edge node. A workflow pipeline with each primitive being implemented by a serverless function has been deployed at the edge and in the cloud for camera 1 and camera 3, and a fifth pipeline has been deployed for camera 2. Users can submit video queries to the controller, which makes a partition strategy in each time slot for all online query according to online pipeline characteristics and available resources on the edge node. The partition strategy is then passed to orchestrate the pipeline execution across the edge node and the cloud. Once complete, the edge and cloud execution information is sent back to the controller for the partition strategy scheduling of the next time slot. The key problem here is how the controller makes the partition strategy. Concretely, the controller contains 3 components. The monitor is responsible for collecting the up-to-date cloud and edge execution information. With the information, the content-aware predictor can forecast some content-varying variables, such as the input data size, edge execution resource demands, and cloud execution expenditure for each function. Based on the prediction results, the scheduler can obtain the partition strategy by efficiently solving a multiple-dimensional, multiple-choice knapsack problem with existing methods. We prototype Serverless with AWS Each primitive in a video query pipeline is implemented as an AWS Lambda function. Data exchanges between functions in a pipeline are via cloud storage service like MMSys and DynamoDB. To extend the execution of AWS Lambda functions to the edge, we install AWLT Greengrass Core SDK on the edge device. The controller is an off-the-shelf host installed AWS IoT Device SDK to enable efficient and secure communication with the cloud and edge functions. Next, let's discuss the evaluation of the system. We obtain the evaluation video dataset from the 2 real-world cameras mentioned in the measurement part, 2 video clips from the crossroad camera, and the 3 video clips from the restaurant camera. Users can issue vehicle query on the crossroad clips and face query on the restaurant clips. During experiments, the 5 video clips are continually streamed to the edge server as if they are captured by 5 live cameras. To enable real-time online decision, the model used by the controller's predictor component should be live, accurate, and fast. After comparing with a wide variety of measures, we choose a multi-layer perceptual model with one hidden layer to achieve the goals. The models are pre-trained on the corresponding camera streams. To evaluate the pipeline analysis speed, we calculate the percentage of the pipeline output frame rate over the pipeline input frame rate, which can be viewed as a normalized throughput. And 100% throughput implies real-time analytics. We also examine the amount of data transferred between the edge node and the cloud, and the monetary costs for executing functions in the cloud. To evaluate the performance of Serverless, we compare it with a pure edge scheme that only relies on functions deployed on the edge node, and a pure cloud scheme only invoking functions deployed in the cloud. We also compare Serverless with a Cisco VM cluster-based Edge Cloud collaborative video analytics system. To make fair comparison, we re-implement it with serverless functions. The main difference between this scheme and Serverless lies in adapting to the video content dynamics or not. We first present a result of querying all streams concurrently for 1 hour. The top figure shows that due to the limited resources, pure edge scheme can't catch up with the input frame rate, thus leading to significant accumulated lags. Although the pure cloud scheme achieves real-time analysis, as can be seen from the bottom figure, its data transfer overhead and cloud expenditure are both high. Benefiting from the Cloud Edge collaborative architecture, SVESC can realize real-time analysis at a relatively small cost. However, as it is content agnostic, it misses the opportunity of reducing cost by adapting to fine-grained video content dynamics. Serverless overcomes the disadvantages of all these measures and hits a best performance. The primary system overhead of Serverless is caused by the predictor and scheduler components of its controller. We measure their CPU consumption when they are serving for all 5 stream queries. As shown in the figure, the predictor consumes about 1.8 CPU seconds per minute, and the scheduler consumes about 1.2 CPU seconds per minute. These overheads are minor for an off-the-shelf host. This indicates the system design of servers is highly efficient and incurs minor overheads, which also provides possibilities for the controller to work efficiently for massively concurrent video queries and a multitude of edge nodes. We further validate serverless scalability and adaptability and unpredictable and bursty input workloads through randomly querying the camera streams. The arrival and departure pattern of queries are shown in the left figure. The corresponding result of servers is shown in the right figure. As you can see, servers always can keep a high throughput and various workloads. When there are sufficient resources at the edge, no cloud functions will be invoked, thus incurring zero costs. On the other hand, when the edge node is handling heavy input workloads, server smartly pushes partial of the workloads to the cloud in order to maintain a high throughput for all online stream queries. That's all. Thank you.